Hi all, today we continue discussing chapter 4. Now we have another example of a surface. This surface is generated from a n minus 1 surface. So first we start a surface as n minus 1 surface in Rn given by S equal to F inverse C, where f from u to r use open subset of Rn with del f p not equal to 0. This is the requirement of the surface. Let We define a new function g from u1. U1 is a subset of Rn plus 1. In fact, that is u cross r. This u is a subset of Rn. So in fact, this u1 is a subset of Rn plus 1. Then function is defined as g of x1 x to xn plus 1 is equal to f of x1 x to etc xn. That means the value, the real number which assigns to this number, this point x1 x2 etc is same as the number assigned to this one x1 x2 etc xn plus 1. Okay, then g inverse C is an n surface. We can say that this is generated from n minus 1 surface. We can easily prove that del g of x1 x2 etc xn plus 1, that is same as this one, and this quantity is up to this now be a zero quantity or zero vector, because f defines a function surface in Rn. So we can say that this never be zero simultaneously. So this is a non-zero vector. Consequently, this will be a non-zero vector. So del g of this quantity is always a non-zero quantity. Hence, this defines a surface in Rn plus 1. So this surface is called a cylinder. Okay. So for example, we can consider a surface f inverse of 1, where f of x1 x2 is equal to x1 square plus x2 square, and this is the circle in x1 x2 plane. I call it is x1, and then this is x2, and this is x3. So this is a circle in x1 x2 plane, this f inverse 1. Now we define g of x1 x2 x3 is same as f of x1 x2 by definition, that is equal to x1 square plus x2 square. So this defines g inverse of 1 is equal to set of all x1 x2 x3 such that x1 square plus x2 square is equal to 1. Okay. This defines at the point when x3 is equal to 0, so we can get this. It's the same circle. When x1 equal to 1, x3 is equal to 1, you can get the same circle at the height 1. Right? Similarly like this. So this defines a cylinder. Okay. So this is one of the examples of this n surface generated from n minus 1 surface. The surface generated by this idea is called a cylinder over S. Okay. Here this S is f inverse C, that is equal to circle. So this is the cylinder over the circle, unit circle. Okay. Now we have a famous theorem. This theorem is called Lagrange multiplier theorem. Let S be an n surface in Rn plus 1. S equal to f inverse C, where f is a function from u to r, where u is a subset of Rn plus 1, open subset of Rn plus 1 with del f q not equal to 0 for all q belongs to S. Suppose g from u to r is a smooth function and p belongs to S is an extreme point of g. What do you mean by extreme point of g? G is that this extreme p is said to be an extreme point of this g. So this g of q is always less than or equal to g of p for all q belongs to S. Okay, likewise our maxima, local maxima, and local minima. We can say that this is the extreme point of the surface. Once you have a surface here, then suppose you have a surface here, then this point is said to be the point of maximum or extrema. We can say that if you choose, this is the point P, we choose other points from this surface as any point. Q is an arbitrary point of the surface, then we can get G of Q is always less than or equal to G of P. Okay, so this is the extreme example for extreme point. Now, or the other way around, we can write this as G of Q is greater than or equal to G of P for all Q. Then this P is also an extreme point. We can say that if G and G has one of the extreme points, then del G of P is equal to some lambda times del F of P. Yeah, this is the idea we need to prove. For that, we will prove this using the idea of the maximum minimum of real functions. This is the proof. We start with a tangent space S at P is SP. This is defined as del FP perpendicular. We already discussed this. Hence, SP perpendicular is the one-dimensional subspace of Rn plus 1 spanned by del Fp. Okay, because this del Fp is this del Fp perpendicular is a n dimensional vector space. If del Fp belongs to Rp n plus 1, we can say that this del Fp perpendicular, okay, this is an n-dimensional subspace of Rp n plus 1. Okay, that is one dimension less than this dimension of the space. Now, if you consider del Fp perpendicular, whole perpendicular. Okay, so when you consider del F of P perpendicular, whole perpendicular, that is always a one-dimensional subspace, because this is an n-dimensional subspace. Then whole perp is an one-dimensional subspace. Okay, that is subspace spanned by del F. That means any vector in this collection is always a scalar multiple of this del Fp. That is the idea here. Then del Gp can be written as lambda times del F of P for some lambda belongs to R. If this happens, you can say that this del Gp belongs to Sp perpendicular. That is if and only if del Gp dot V, that means it's an element of this, dot product is 0. So in order to get this, we need to prove that del Gp dot V equal to 0. That is enough. Okay, once you prove this for all V belongs to P, you can say that this is an element of Sp perpendicular. Consequently, we can get del Gp is equal to lambda del Fp using this idea. Okay, so we start with a velocity vector V belongs to SPs of the form V is equal to alpha. Our intention is to get this del Gp dot V equal to 0. That is once we need to prove. So we start with the vector V that belongs to Sp, that is a tangent space of P, tangent space at P. Then V is a velocity vector of some parameterized curve, say alpha dot T naught. Then and this alpha is a parameterized curve from some open interval I to S, and T naught belongs to I with alpha of T naught equal to P. Since P is an extreme point of G, T naught is an extreme point of G composition alpha. Okay, we know that this G is a function from U to R, and alpha is a function from I to U, or we can say that this G is a function from S to R. Instead of this U, we have S to R, and this alpha is a parameterized curve from I to S. Then once you consider G composition alpha, that is always a function from the domain of the alpha to the codomain or range of this G. Okay, range of this G is R. So we can say that G composition alpha is a real valued function defined on a open interval. Okay, so if P is the extreme point, once you consider this G of alpha of T for all T, okay, so we can get G of Q such that Q is equal to some alpha of T. We know that this g of k is always less than or equal to, this g of p is the, here we have t naught, so g of t naught is also belongs, g of alpha of t naught is also an element of this domain, right? So we can say that once you consider set of all g of alpha of t, we can say that at least it contains a point g of alpha of t naught, that is g of alpha of p, sorry, g of p, and for any g of q, we have g of p has the extreme value. So we can say that this g composition alpha has the extreme value at the point t is equal to t naught, because at the point t is equal to, at the point t is equal to t naught, because g of t naught, g of alpha of t naught or g of p has the maximum or extreme values. There. So using the idea of the real function, whenever this a real function, a smooth real function, that means differentiable real function, has maximum value, at that point we have the derivative of that function as 0. So we start with 0, that is equal to g composition alpha dash t naught, that is decomposition alpha, derivative of this function at the point t equal to t naught. So this is nothing but del gp dot alpha dot t naught, that we have already discussed, d by dt of g composition alpha. Using the chain rule, you can get that is del gp dot alpha dot t naught. So this is actually, this p is actually alpha of t naught. Okay, so this will be del gp dot v for all v belongs to sp. So we have that quantity is equal to 0. Consequently, del gp dot v equal to 0. Whenever del gp dot v equal to 0, we can get del gp is equal to lambda times del fp. Del gp is a multiple of del fp. So this shows that whenever g attains an extreme value at p, we can say that the gradient del gp is a lambda multiple of del fp. This is the idea. So now we have some remarks. If S is compact, we know that every smooth function defined on a compact set attains its extreme values. So if S is compact, then G from U to R attains maximum and minimum on S. The theorem above can be used to evaluate such points with the condition del Gp is equal to lambda del Fp. If S is not compact, there may be no extrema. With this, we completed the chapter 4, and the next class we will discuss chapter 5, the vector fields.